So in this lecture, we are going to see power series solutions. So let me start with some basics of this chapter. So let us write some initial notes. Now all of us know that 1 upon 1 minus x, this can be written as 1 plus x plus x square plus x cube plus so on, but here x should lie between -1 and 1. X cannot be equal to 1, otherwise this denominator will become undefined if I put x equal to 1. Similarly, if I write 1 upon 1 plus x, then it will be equal to 1 minus x plus x square minus x cube and so on, where -1 is less than x less than 1. The third thing that we know is the Taylor series for sine x. What is the Taylor series for sine x and the Taylor series for cos x? It is x minus x cube upon 3 factorial plus x raised to 5 upon 5 factorial and so on, with alternating plus and minus signs. And what is the cosine function? The Taylor series of that is 1 minus x square upon 2 factorial plus x raised to 4 upon 4 factorial and alternating plus and minus signs with even powers. And these two Taylor series are valid for all x in real numbers. Fifth Taylor series that we should know is e raised to x. What is the Taylor series for e raised to x? It is 1 plus x square upon 2 factorial plus x cube upon 3 factorial plus so on, and e power minus x. If I just replace x by minus x in the above thing, it will get 1 minus x plus x square upon 2 factorial minus x cube upon 3 factorial plus so on, and both these Taylor series are valid for all x in R. So these are some standard Taylor series that we are going to need in this particular chapter, which can be written in the form of summation x power k going from 0 to infinity. The second thing can be written as x power minus 1 power k, because there is alternating plus and minus sign, x power k going from 0 to infinity. Sin x can be written as -1 power, let us decide that, which is x power 2k plus 1 upon 2k plus 1 factorial, where k goes from 0. If k goes from 0, I will get x raised to 1 upon 1 factorial. With -1 sign is not there, I have a plus sign in this, so it will be -1 raised to k plus 1 for k going from 0. So if you now put k equal to 0 in this expression, I'm sorry, this is not k plus 1, this is k will do the correct job. -1 raised to 0 is 1. So -1 raised to k, x raised to 2k plus 1 upon 2k plus 1 factorial. What about the fourth power series? In the summation format, it can be written as -1 raised to k, because if I put k equal to 0, I'm going to get a 1, and x raised to odd, x raised to even power, x raised to 2k upon 2k factorial. So automatically I will get, when I put k equal to 0, I will get 1 everything, and when I put k equal to 1, I will get -1 and x raised to 2 upon 2 factorial, which is the second term. When I put k equal to 2, I will get x raised to 4 upon 4 factorial, and this is how it will continue. What is the power series? What is the power series expansion for e raised to x in summation format? It is very easy. It is all terms are positive, so it is k going from 0 to infinity x raised to k upon k factorial, which is, if I put x equal to 0, I will get 1. If I put k equal to 0, I will get x upon 1 factorial, which is x, and then x square upon 2 factorial, and so on. Here in the last expression, again I have, here in the last expression, I have all alternating plus and minus signs. So I will get k going from 0 to infinity minus 1 raised to k into x raised to k upon k factor. Okay, so these expressions are compact forms now. So suppose in future I come across with some summation which is looking like this, I can directly replace this by what I will say, that it is nothing but your sin x. So let us see in the coming lectures that will we be able to do such types of things. Okay, now let us see what is meant by ordinary point. So let us now define what is meant by ordinary point. So I will take a general differential equation. So let b naught x y raised to n, this is the nth derivative, plus b1 x y n minus 1th derivative, plus so on, plus bn minus 1 y dash plus bn y equal to rx be a differential equation. Okay, and these b naught, b1, they are what? They are actually functions of x. So I'm writing differential equation where these b naughts, b1, they are all functions of x. Right, now I will look at a point x naught. So if x naught is a point such that I will look at the first coefficient, the highest derivative coefficient. Who is that first coefficient? b naught x. X naught is point such that when I substitute that x naught in the first function, and suppose it is not equal to 0, okay, then means x naught is not the root of this particular coefficient b naught x, then x naught is said to be ordinary point. Okay, I will repeat it again, to be ordinary point. So let us take one simple example for that to understand what is the ordinary point. So example, let me take a differential equation, 1 minus x square into y double dash plus 2x y dash plus y equal to, suppose I take sin x. Okay, now what is here the highest coefficient? So here the highest coefficient, the coefficient of the highest derivative. Okay, here 1 minus x square is equal to, suppose I put equal to 0, then I will get x is equal to what? X is equal to plus minus 1. So we know that at x equal to 1 and x equal to minus 1, what will happen? This 1 minus x square, which is this function b naught x, okay, will become 0, will become 0. So this means that x equal to 1 and x equal to minus 1 are not ordinary points, because for ordinary points what should happen? For ordinary point it should not be equal to 0. So if x equal to 1 and x equal to minus 1 are not ordinary points, then who are the ordinary points? So all remaining points will become ordinary points. From the all real numbers, 1 is not allowed and minus 1 is also not allowed, because they are not ordinary. So now who can become ordinary? Is x equal to 0 ordinary? So the answer to this question is yes, because if I look at 1 minus x square and if I put x equal to 0, I will get 1 minus 0 square, which is 1, so that is not equal to 0. Is x equal to 2 ordinary? So the answer to that question is also yes, because if I put it in 1 minus x square, it will become 1 minus 2 square, which is minus 3. So that is also not equal to 0. So what you understand is that identifying ordinary points means what? You first identify what are not ordinary, and then all remaining points will become ordinary points. Sometimes it is like this. Suppose I take one more example. Suppose I take an example. Let me look for a better example now. Okay, suppose I look at this thing: y double dash plus 2x y dash plus y equal to cos x. Okay, now who is the coefficient of the highest derivative? Here the function b naught x, which is the coefficient of highest derivative, is 1. Okay, now this thing will not become equal to 0 for any x, because there is no x inside it. So it is not equal to 0 for any x. So this means that, what is the thing? There is no all the points of all the real numbers x will become my ordinary point, because it is never equal to 0, right? So all x in the real line are what? Are ordinary points, right? Let us take one more example for clearing the concept more. Suppose I look at this particular equation: x y double dash plus x y dash plus y is equal to 0. Then I understand that this person will become 0, so that function b naught x, which is x is 0. If when is x equal to 0? If the value of x is itself 0, means the in real line only 0 is not allowed as a ordinary point. So this is not ordinary. Okay, so who are the ordinary points? Therefore all non-zero real numbers, all non-zero real numbers are what? Are your ordinary points, right? So we should really give a name to such points which are not ordinary. Okay, and what are such people called, which are not ordinary? Such points are called singular points. So that gives us the definition of singular point. What is a singular point? X naught is a singular point of above ODE of the above differential equation, which we have mentioned above, if b naught, when I substitute x naught, will become equal to how much? Will become 0. So if x naught is a root of that first person, then it becomes a singular point, and if it is not a root of that first coefficient b naught, then it is said to be a ordinary point. So this is very simple. Let me take one simple exercise and just identify what are the singular points. So okay, so let us take one example. Find singular points of x into 3 minus x y double dash minus 3 minus x y dash plus 4y is equal to sine x. So here, what is the coefficient b naught? So solution: coefficient b naught is x into 3 minus x, and this is equal to 0 if what? If x is equal to 0, or 3 minus x is also equal to 0. So this means x is equal to 0 and x is equal to what? 3. So these 2 points are your singular points. So suppose I take y equal to summation an x raised to n goes from 0 to infinity. Now this means that y is equal to, put n equal to 0. When you put n equal to 0, you will get a0 x raised to 0 plus a1 x raised to 1 plus a2 x square plus a3 x cube and so on. This is called as a power series. So let us write the derivative of this y. So y dash is equal to, I'm differentiating this, okay, summation an into n x raised to n minus 1. Okay, and I will write here n goes from what, 0 to infinity. When I take the actual derivative of this person, y dash will be equal to what? What is the derivative of this? This is a naught into 1, correct? So the derivative will become 0. And this is a1x, right? So the derivative here will be a1x plus a2x square, a2, so this a1x, a1 will be as it is, then this a2 into 2x plus a3 into 3x square plus dot dot dot, correct? So this summation which I am writing here, I understand that when I actually put n equal to 0, what will happen? When I put n equal to 0, I will get a0 into 0 because I am putting n equal to 0. So this a0 term will never occur in the summation. When you put n equal to 1, what will happen? I will have a1 into 1 into x raised to 0. Okay, see, this is matching here, right? Plus when I put n equal to 2, I will get what? a2 into 2 into x raised to 1, which is exactly matching with here, correct? So this means that when I'm going to put n equal to 0, this term will not be coming in the picture because it is 0. So then why am I writing summation from n equal to 0? So it is better if I write that summation instead of writing from n equal to 0, I will directly write the summation from what point? I will directly write the summation from n equal to 1. Because at n equal to 0, anyways it is giving me 0 term, so it is useless. So I will just remove that. So I will write here an x raised to, an into n into x raised to n minus 1. Okay, so I hope this is understood why I converted the summation from n equal to 0 to n equal to 1, because at n equal to 0 it was giving me anyways a 0 term now, and it matches with the lower person. Now what I am interested in is I want to convert this particular summation, okay, I want to convert it, this summation in such a form that this particular term of n minus 1th power should look like an nth power. So what changes should I make here so that this x raised to n minus 1th power will start looking like x raised to n? So what I will do is I will simply put n minus 1 is equal to k. Okay, I'm just doing it substitution like integration. Put n minus 1 is equal to k. If I put n minus 1 equal to k, this means that n will be equal to k plus 1, right? Let us look at the limits. What are the limits? If n is equal to 1, this is the lower limit, okay? If n is equal to 1, This means what will be k equal to, if n is equal to 1, k will be equal to 1 minus 1. So at that point, k will become 0. I am repeating this. The lower limit is n equal to 1. If n is equal to 1, this expression will give you that k is equal to 0. If n tends to infinity, this same expression gives you that k also tends to infinity. Therefore, the above summation in the new variables k will start looking like n equal to 1 will get replaced by k equal to 0. Infinity, n equal to infinity is k tending to infinity. So these two are solved. What about the inside term? Now remember, inside there should be k's because we are changing the variable. So n should be replaced. So it will be a, n should be replaced by what? N is k plus 1. So a k plus 1 into n, which is again k plus 1, into x raised to n minus 1. N minus 1 is how much? N minus 1 is k. Right? So the same expression has, after a change of indices, is looking in the form of ak plus 1 into k plus 1 x raised to k going from 0 to infinity, and this k is going to change. So if I replace this k by any other variable, still the meaning will remain same. I mean to say that if I replace this k by m, what will this expression look like? It will look like m going from 0 to infinity, am plus 1 into m plus 1 into x raised to m. So k is just replaced by m. So if I am replacing k by m, I can replace k by any other variable. So instead of replacing by any other variable, why are we not replacing k by just n? If I replace the k by n in this expression, what will happen? After the change of variable, I am replacing the k again by what? I'm replacing the k by n again. So what will that expression look like? This, okay? Summation n going from 0 to infinity, a n plus 1 into n plus 1 into x raised to n. So now I hope you have understood that we have achieved what our target was. Okay, so if y is summation an x raised to n going from 0 to infinity, then we will find expression for y double dash. Okay, and that expression of y double dash will be such that it will involve x raised to n in its summation. Okay, so clearly if I write y dash, if I just take the derivative of this, the derivative will become n from 0 to infinity an into n x raised to n minus 1. And what is the double derivative? Y double dash is equal to summation 0 to infinity n into n into n minus 1 x raised to n minus 2. Now here you understand that if I put n equal to 0, this entire expression will become 0. If I put n equal to 1, again the entire above expression will become 0, correct, because n minus 1 will become 0. So in this summation, n equal to 0 and n equal to 1 will contribute what? If I put n equal to 0, I will get 0. If I put n equal to 1, I will get 0. And from n equal to 2 onwards, everything will remain in the addition. So from n equal to 0 and 1 are of no use because they are giving me the value of that expression is becoming 0. So I will say n goes from 2 to infinity, okay, an into n into n minus 1 into x raised to n minus 2. So this will just simply become, I will just write the summation n going from 2 to infinity, n into n into n minus 1 into x raised to n minus 2. But again, as I told you that I'm not liking this term. This is x raised to n minus 2. So I will make a change of variable. So I will put n minus 2 equal to k. And I put n minus 2 equal to k, then this means that n will become what? N will become k plus 2. Now what are the limits? If I look at the limits of the summation, for the limits, n is equal to 2. If n is equal to 2, at that time, this expression will tell me that k should become equal to 0. If n tends to infinity, then again the same expression tells me that if n becomes large, k also becomes large, and therefore the above summation in the change of variables will get changed to summation lower limit k going from 0 to infinity a n is to be replaced by k plus 2, a k plus 2 into n is again k plus 2 into k plus 2 into n minus 1. N minus 1 will become k plus 1 because I'm subtracting 1 from both sides, x raised to k. And therefore I see that this k is nothing but called as a dummy variable. Dummy variable means I can replace the alphabet k by any other alphabet, and that alphabet is what I will replace it by. So just replace the alphabet k by n. So that is called as a dummy variable. So n is going from 0 to infinity, a n plus 2 into n plus 2 into n plus 1 into x raised to n. So this becomes the expression for the double derivative, which is involving what? Which is involving x power n. And if I recall what was the expression for the derivative, y dash was summation n going from 0 to infinity a n plus 1 into n plus 1 x raised to n. This was the expression for the derivative, and the expression for original y is what? That is our original power series, which is a n x power n going from 0 to infinity. So these three expressions will help us to some extent in solving our problems. Okay. So question: solve y dash minus 2y equal to 0 by power series method. Okay. So I will say that let y be equal to summation n going from 0 to infinity an x raised to n, which is our power series. And therefore what is y dash? And therefore y dash is summation n going from 0 to infinity an into n x raised to n minus 1. I will change the variables. N minus 1 is equal to k. So in this change of variables, the derivative expression will become n will become k plus 1. This will become ak plus 1 into k plus 1 into x raised to k, and so and the limits of the and the limits of the summation will become k going from. So this we know that this summation actually makes sense from 1 to infinity, because at n equal to 0, the value of the the term is 0. So this means k will go from 0 to infinity, but k is a dummy variable. So I will replace k by n. So this means y dash will be equal to summation n equal to 0 to infinity an plus 1 into n plus 1 into x raised to n. This expression we have obtained in the above section, the same expression. So we have an expression for yn here and we have an expression for y dash here. Now we will go to the original differential equation. What is the original differential equation? It is y dash minus 2y equal to 0. So consider the differential equation y dash minus 2y equal to 0. So what is y dash? Y dash is summation n going from 0 to infinity an plus 1 into n plus 1 x raised to n minus summation n going from 0 to infinity to an, because this 2 is multiplied, to an x raised to n equal to 0. Okay, because y was what? Y was summation an x power n. Now I see that this x power n is here, both of them. Summation is going from, the summation limits are also the same. So I can make this summation as a compact form, n equal to 0 to infinity with an x power n outside. Now here we are very lucky that the summation limits are also the same. In the coming problems, it will happen that the summation limits will become different, but our target will be that we have to always write the summation in form of which involve x raised to n, so that we can take x raised to n common. So here what will I get inside the square bracket? I will get an plus 1 into n plus 1 minus 2an. Okay, on the right hand side we have a 0 thing, which is a 0 power series, so it is equal to summation n going from 0 to infinity 0 into x raised to n. So now I will compare the coefficients. So if I compare the coefficients, what will I get? I will get an plus 1 into n plus 1 minus 2an is equal to 0. And this becomes an plus 1 into n plus 1 is equal to 2an, and therefore when I calculate an plus 1, which is 2an upon n plus 1. Okay, so here an plus 1 is expressed in terms of its previous terms. Its previous terms. Who are the previous terms? An. Such an expression or such an equation is called a recurrence relation. Okay, this is called as a recurrence relation. Now let us put n equal to, now we know that what were the values of n? The value of n was varying from what? The value of n was varying from 0 to infinity. So let us put what is what if n equal to 0? So let me put n equal to 0. So put n equal to 0. We'll get a is 1. So this expression, put n equal to 0 here. You get, put a1 is equal to 2a naught upon 1. So a1 is 2a naught. Now you put n equal to 2. Sorry, n equal to 1. When you put n equal to 1, you will get a2 is equal to 2a1 upon 2, which is a1, but I will not cancel this 2 right now. Okay, I will not be in a hurry to do that. So it will be 2 upon 2 a1. What is a1? But a1 is 2a naught. Put n equal to, see, remember in this calculations, do not cancel immediately, otherwise you will land into problems. Put n equal to 2, put n equal to 2, we get a3 is equal to 2a2 upon 3, which is 2 upon 3 a2. What is a2? a2 is 2 upon 2 into 2a naught. Okay, see, observe these terms. Okay, what I want to teach you is that since I've not cancelled, can I write the general form, or can I now, without doing anything, can I tell what will happen if I put n equal to 3? Guess that. Look at this observation. If it is a3, here it is 3, 2, and then there is a 1. If it is a2, there is 2 and there is a 1. If it is a1, there is 2 upon 1. I should have not even forgot this one. Okay, so if it is n equal to 3, I will get a4 is equal to, the denominators will now have 4, 3, 2 and 1 pattern a naught. And what will the numerators have? But all the numerators are 2. So you'll have a 2, you'll have a 2, have a 2, and you have a 2. So in general, if I look for an, what will happen for general an? It will start at n minus 1 dot 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 3, 2, 1, and you'll have 2. How many times will you get a 2? You get n times 2 into a naught. Can I write this expression in a bit compact form? This is 2 raised to n, because you'll have this 2 is n times, the denominator is n factorial into a naught. This is the expression for an. So this an, which is depending on a naught, is the final expression of an, and therefore now I will substitute this an in the power series. So substitute in y. What was y? Y is equal to summation n going from 0 to infinity n x raised to n. Now you understand that when I'm solving by the power series method, what is our target? Our target is to find this an. This an we wanted to find. To find this an, you have to actually solve this recurrence relation. Okay, if you know a little bit about recurrence relation, the method that I have solved this recurrence relation is called as iterative method of solving a recurrence relation. You take and put n equal to 1, put n equal to 2, back substitute, and then you get the general form of the solution, which is called as iterative method of solving a recurrence relation, right? So we have got this general solution of by iterative method, and that I'm going to substitute in y. So it is equal to summation n going from 0 to infinity an. What is an? I'm going to substitute it here, 2 power n upon n factorial a naught into x raised to n as it is. So here it is an, I've substituted an, and here I've written x raised to n as it is. This is equal to summation. Do you see that this a naught is a constant and it has nothing to do with the summation, because the summation is related to what? Summation is related to n. So for whatever quantities are involving n will remain inside the summation. All other people which do not involve n will come out of the summation smoothly. So this a naught will come out of the summation, and what remains stuck inside the summation is 0 to infinity 2 raised to n into x raised to n upon n factorial. This 2 raised to n into x raised to n, I can write it in more compact form, which is n equal to 0 to infinity 2x raised to n upon n factorial from 0 to n. Who is this? This is your y. Now, in the first part of this lecture, I have already told you about the Taylor series of e raised to x. What was the Taylor series of e raised to x? The Taylor series of e raised to x was x raised to n upon n factorial, n going from 0 to infinity. So what is the Taylor series for e raised to 2x? Just replace the variable x by 2x. It will become n from 0 to infinity 2x raised to n, because x is just replaced by what? 2x. So this is 2x upon n factorial. So this means that this y, I'm sorry, I forgot a naught here. This means that this y, which is a naught into summation 2x raised to n upon n factorial, is nothing but a naught into e raised to 2x, because we know that this particular thing is nothing but the Taylor series of what? It is the Taylor series of e raised to 2x. So this is recall. So this means that our solution of which differential equation? The differential equation was y dash minus 2y is equal to 0 is given by what? Is given by y equal to a naught e raised to 2x. This becomes our final solution by the power series solution method. What we have done, we have solved this problem y dash minus 2y equal to 0. So if I replace this 2 by a, where a is any real number, then what will I get? So I will proceed the same way it is by saying that y is equal to this, and y dash will become this expression, and then I will get I'll change the variables and I will substitute the same thing in this differential equation. Instead of y dash minus 2y, I will get here a. So the story will continue in the same way, and this 2 will also get replaced by a. Here also I will get an a into an, and then the recurrence relation that I will get is a into this, which is a into an, which is these changes will be there. So wherever I get a 2, wherever I'm getting a 2, all those 2's will be replaced by that constant a. Okay, so this will become a into a into a. In general, I will get a's here. All 2's are replaced by a, and therefore this will become a is equal to a raised to n into a naught. When I substitute it here, I will get a raised to n a naught a raised to n x power n. This will become ax raised to n, and I will get a naught e raised to ax.